Okay, so we've got beam, and it's just one of these again, 30 centimeters long, rotating about an axis through its center on really good bearings. And we got a magnet centered at this end, and another one centered at the very tip on this end. Okay. And then halfway between the center and the edge, we got a stack of 3 magnets here. So imagine 3 magnets and a stack of 3 magnets here. And we want to calculate the moment of inertia. Well, we know, and everybody's doing this. I think everybody's got it right. I checked, you got the MR squared for every one of them. So what we have is moment of inertia of the beam, calculated it in my head, and I got this. I won't swear it's right, but I think it might be. And I did that calculation last time, so you know I was checking. Okay. I'll probably go ahead and do it here. Okay, so it's what now? You got a 50-gram mass here and a 50-gram mass here. Well, that's a total of 100 grams times 0.3 meters squared. Okay. And then here you've got a total of 600 grams, 300 grams, sorry. Doubled it too many times. Okay, well, 100 grams times 0.3 meters quantity squared is oh 09 kilogram meters squared. Your numbers seem to agree with that. Did you get like a 0.0045? This is going to be 300 times 0.225, 0.0225, 0.3 times 0.0225 is 0.025 times 0.3. That's about right. Okay. Those numbers make sense? We agree? Where's my, is my brain not clicking today, which I suspect to be the case. Took a while for people to tell me what they got, even though they had a calculator. You know, a lot of people just did the total. I think it's instructive to see what the individual moments of inertia are for 2 magnets out here and for stacks of 3 magnets here. You get more moment of inertia from the 2 magnets on the end than you do from 6 magnets halfway to the end because of the R squared thing. And that's really worth thinking about. Okay. So if you just want to get the answer, yeah, you put it all in, you put it in a spreadsheet, you get the answer. It's often, and I'm not saying you did anything wrong, it's often good to look at the individual numbers when you have something like this, so you get a better understanding of what the moment of inertia is telling you. But that's not going to be moment of inertia of the beam. Well, it's this. Now, I probably round that off to 0.016 because there's plenty of uncertainty and exactly where I positioned those. But I was actually pretty good. You know, when I did it, just eyeballing it, I just almost nailed one of them, and I was only off a couple of millimeters in the other. And I forget which side it was on. But the 7.5 is probably insignificant. The 5 is certainly insignificant. Okay. So you want to think about what your significant figures are. Now, moment of inertia of the beam. It's a formula. It gives you this. It's 1/12 big M L squared. Okay. If I square this, I get 0.36. And that, okay, I'm off by a factor of 4. That should be 0.006. I know what I did. I squared the 0.3 when I did that because I wasn't thinking clearly. As I warned you in the first place. Okay, so we got 0.36, 0.072, 0.006. Yep. Okay. So now we can replace moment of inertia of the beam by what 0.006 kilogram meters squared. You do it up here too. And we can look at the numbers. This is about the same as this, but the magnets at the middle have a total moment of inertia greater than that of the beam, okay? Which in some ways isn't surprising because they have 50% more mass, but they have half the distance to the end, okay? So you want to think about that. You just kind of want to think about the, okay. So there we have it. So now the question is, this thing's accelerated. It passed a fully diameter 5 centimeters. Rotating with the beam. If it descends 40 centimeters, what can you determine? Okay, now, a lot of people have a couple of formulas, you know, I see an omega R there. And I see one half I omega squared, which is a pretty good hint. Okay. Of course, what the formulas mean, well, you want to think about what they mean. This is just an expression of what a radian means. Okay. And that's just something we derived last time. Your moment of inertia is your sum of all your MR squareds. And when you multiply that by your omega squareds, you get the sum of all your MV squareds. You have the 1/2 the sum of all your MV squareds. You should ideally be able to make that connection. Every time you see that formula, you should be able to see the connection with 1/2 MV squared. We spelled that out last time. Just makes it more believable, gives you a better grasp of what's going on. Okay, descent is 40 centimeters, implies okay. You got a 50-gram mass, that's a 0.5 Newton weight. There's descending 0.4 meters. Okay, 0.5 newtons through distance of 0.4 meters gives you 0.2 joules. Okay, I think. Delta Y is negative. This is the work done by the gravitational force. This is the negative of the work done by that conservative gravitational force. I want to keep harping on that idea because it's going to be important in other aspects of the course, starting in a week or so, especially gravitation stuff. Okay, so we get that. That should be minus 2 joules. What's going on? Oh, yeah, this is positive. Gravity's downward, delta Y is downward, so the work done by gravitational force is positive. So change of potential energy is equal and opposite. It's negative. Okay, you know the potential energy is decreasing, but you want to connect that rigorously with the definition of change of potential energy. Okay. I can use just good old MGH if you want to. I say avoid it if you can. Okay, because it's going to pollute your mind when we start talking about orbital velocities and stuff. Okay, in the gravitational field of the Earth. And it really pollutes people's mind. We can get into electromagnetism, they're still trying to use MGH for potential energy. Okay. So I kind of despise that formula. Equal and opposite to the work done by conservative force, period. Okay. So again, use it if you want, but make sure you understand that it only applies to very, very limited range of situations in the immediate vicinity of the surface of the Earth. Okay. Okay, well, anyhow, there we have it. So there's your change of potential energy. Well, what can you determine from your change of potential energy?
Change in kinetic.
Here's a ventriloquist in here, somebody in the hall throwing their voice, made it look like it was coming from Stosh over there in the class. Okay. But yes, it's conservation of energy. If you neglect non-conservative forces, and they're pretty negligible in this case, then of course that's one of the things we're trying to get a handle on with the experiments. You find that the kinetic energy has to increase by half, by 0.2 joules. Okay. Now, if it started from rest, which it implicitly did, because it always has when we've done it, we didn't state that, right? So I'm going to erase this because I did it last time anyway. Yeah, I know you're in a hurry with all the problems that have been assigned and everything to get them done. But take an extra 10% and write some words around them to reinforce what's going on. Assuming negligible conservative forces, you can abbreviate that. Okay. FC, conservative, non-conservative forces. See, I write it out and I write something misleading. You can write something like F and C equals 0 implies. Okay. And that would reinforce for you the assumption. And remind you that there are actually conservative forces that we might be able to measure. Matter of fact, I'm going to show you in a minute how we could measure it. Because I did something really neat with the cart and the incline that I'd never thought of doing before. I figured out that the coefficient of friction on that cart is about 0.006. Rolling friction. Okay, so we'll be able to figure out what the friction is here. Using a similar thing, you'll see. Okay, so again, this is an important assumption to document in your work. It reminds you of what's going on. But this then implies that I'll use delta K and delta U because those are the symbols that your book would use. So if you know what the change of potential energy is, change of kinetic energy is equal and opposites 0.2 joules. Now you get used to doing that, and sometimes you just say, well, the change of kinetic energy and change of potential energy are equal and opposite. That's true as long as this is true. Okay. So I didn't want to write a net on that. Add up all the non-conservative forces. Okay. Okay, well, anyhow, there we have it. So what's a change in kinetic energy? One half I omega F squared minus one half I omega naught squared. That's just one half mv squared for rotation. Showed you why last time. You want to understand that. This is 0 by assumption. It's not always 0. You write down from rest. You could even write down the word rest. But that shows that you've taken account of the fact that maybe that initial velocity isn't 0. Okay. Okay, so what do we do now? Well, there's your I. All from omega F. Makes sense? Excellent. Omega F equals the square root of 2 delta K over I. You do the dimensional analysis, and if you do that off to the side, then you don't necessarily have to write the dimensions on every number you plug in here. Okay? You can say change of kinetic energy is going to have units of joules, which is kilogram meter squared per second squared. I has units of kilogram meter squared, so the kilogram and the meter squared go away, and you end up with reciprocal seconds squared under the square root. So you end up with reciprocal seconds, which you interpret in this case as radians per second. So you got to be careful about your dimensions. I've seen on the test and other places, not from everybody, but from most people did at least one bonehead dimension error. And I say bonehead because you see me making similar errors. Not being insulting with that, we're all boneheads. if we try hard enough, okay? Doesn't mean egregious. Egregious is really bad. Bonehead is just, oh man, what did I just do? Okay? Check yourself. Now, 2 delta K is 0.4 joules. Divide 0.4 joules by 0.02175. That's about like multiplying by 50. Okay. And if you take 0.4 multiplied by 50, you get 4, and take the square root, you get about 4. Now that seems way high, so I think I did something wrong with my numbers. If I multiply by 50, 0.4, 0.4 times 50 is 20, gives me like 0.45 radians per second. And I don't think it's going to go that fast. We're going to find out in a minute. Okay, so I'm going to check my prediction against the reality. I'm pretty sure my theory is right here. I'm not sure I got the right numbers because I did a lot of it in my head, which isn't working. It's working even worse than usual today. Okay, so let's go ahead and do this. I'm going to pause the video. So a moment of suspense. Okay, for anybody who is not here today, because I think one person is, so. Has to be filling the balance. It's another magnet there. Anybody see a magnet? There's one. Gotta be. Like perhaps it's reproducing here. Okay, so here we have the beam. And I don't know how well we're going to be able to demonstrate what happens, but do my best. Okay, and we bring the magnet close here. Then we release it and it starts rotating. Okay, so I'll just simulate it. It rotates out about like this. Then it comes back. And the magnet's still here, so it repels again. It rotates and comes back. It repels again. It rotates and comes back. Of course, it's losing energy, so it doesn't go as far each time. It's losing energy to friction. Now, when we had it on this rotation apparatus with a good set of bearings, did 50 cycles of that. And it went out to about 90 degrees. Got kind of close to what I think I did when I demonstrated it. Or I attempted to demonstrate it. It wasn't a great demonstration. So magnetic potential energy went into the kinetic energy of the beam. Okay. From the distance it went before it came back. Well, another thing we had the descending mass on it. We still have the descending mass, which is why the thing stops. If I didn't have the descending mass, it would go through a bunch of revolutions. Okay. Well, let's see how that works. Negative PE goes to the kinetic energy of the beam. Beam rotates until friction. And potential energy gain, because as the thing rotates, that mass is rising. Writing out a bunch of stuff for anybody's watching. I hope you can read it because I'm writing kind of fast. Okay, so magnet potential energy gives the kinetic energy. Immediately, the descending mass starts ascending, right? The hanging mass starts ascending, which sucks out your kinetic energy, and friction does a little bit, okay? Comes back, well, gets out, it comes to rest, and then the hanging mass is going to pull it back. Comes back, gets repelled by the magnet again, and the whole thing starts over, and it keeps going back and forth. Fifty times the rest, okay? Initial displacement was 90 degrees, pretty close to 90 degrees, which is 1.5 radians ballpark. A little more than 1.5, but we won't worry about that. So I asked everybody to graph the displacement, and I should put the word angular. That's an ANG there, meaning angular displacement. You can't read it. So we have 1.5. So I have to put units in that 1.5. We label the y-axis with units. We know this means 1.5 radians. And number of cycles. Okay, cycles out and back. And you get a graph that looks something like this, where it reaches 0 at 50. Okay. Now I want to know the total angular displacement. Okay. Can you estimate what the average angular displacement was based on your curve? Okay, now most people, as usual, this is kind of predictable. We've talked about it before, so you need to get over it. Okay, most people are drawing the thing about halfway between here and here. So most of the thing is the average displacement here. Well, here's how much area lies above this line, okay? And here is how much area lies below this line. This is the area that you're giving the displacement credit for that isn't really there. This is what you're leaving off, what's really there that you're not counting, okay? You can think about that. You can look at the pictures in the book. I think it's a very good picture of an average value in your text, okay? Nice colored picture, much better than anything I could draw. Something you should have learned when you're processing the idea of the average value of a function in calculus by integrating it and dividing by the length of the interval. Okay? But people never do. They don't do it when I teach the course. They don't do it when anybody else teaches the course. And it's a cognitive problem that I know how to solve, but it drives people crazy, and then we got to pay their mental health bills. No, uh, it's a difficult concept. Okay, so here we go again. Here's a curve. Now I want to draw the average value. What I'm doing is I'm trying to construct a rectangle. Area between here and here is equal to the area under this curve. Now, how did I do? Actually, that came out a little better than I thought. That might be a little bit low on that one, but my curve is a little less concave. That area looks pretty comparable to that area. I can't really say for sure which one's greater. When I look at it from this angle, one of them looks greater. When I look at it head on, no. Okay. So maybe I kind of did it fairly close. So if this is 1.5, what's this? I'm going to say this is about maybe 0.5. Okay. Now you don't really know what the curve is. You could do video and you could see the angles, you can make marks and stuff like that. Or just get out here close to the system and keep ballparking it. Okay, like if it rotates from here to here, that's about 90 degrees, that's about a radian and a half, right? If it rotates a distance along the arc equal to the radius, then that's about maybe this far, about 60 degrees, okay? So you could even estimate in degrees. How far does it go from here to here? You can estimate that within 10 degrees, probably within 5 degrees. If you got any kind of an eye at all. Not everybody does. Not every engineer has a good eye for estimation. But they have other skills. People who do have a good eye for estimation might not. Okay? It balances out. You get through the engineering program at Virginia Tech, you've got some skills. Okay? If one of them is estimation, great, that can be very handy. The other one's analytical, that's great, that can be very handy. If you actually understand some physics, that can be useful too. That's, of course, what we're trying to accomplish here. Okay, so now my question is, what was the total angular displacement? How did I miss that? Was it my reflexes? Was it that I'm not warmed up? Shouldn't make a difference. Okay. So what's the total angular distance? We can say that this is the average I'll read it to you in case you can't read that, because I'm writing pretty fast. Average angular distance out is 0.5 radians. The total angular distance out is 0.5 radians per cycle times 50 cycles. And you want to write radians per cycle times cycles to make sure that you're doing something that makes sense. The units should be working out. There are always units. Well, not always. Some things are unitless. Okay, so you get a total of 25 radians. Well, that means you got about 25 radians back. Now back is a little less than out because it doesn't get quite as close to the magnet as it started, okay? So you might say, okay, it's about 24. It gets pretty close to the same distance, okay? So I'm going to say back is about another 25 radians, maybe a little less. But that's 50 radians. Okay. So it had to go through 50 radians, which is like eight and a half cycles, probably about eight. About 8 cycles completely around before it lost its energy to friction. Well, we can go further with that. There are further questions we can ask. I'll be asking them. Okay. So you could ask a question like, what's the equivalent of a angular coefficient of friction? What would that mean? Okay. Well, this isn't that good of a measure of the angular coefficient of friction because my fingers were holding that magnet. I had my hand pretty firmly down on the platform there. Okay. So I don't think it was moving much, but it could have moved a little bit. Could move that magnet a little bit to increase or decrease the potential energy. Okay. And my fingers, they're kind of bony, but they're a little bit squishy. Okay. So there's energy in squishing and unsquishing the tips of my fingers. Okay. So to really do this, we would want a very rigid support. It is difficult to do that. Just put down a few kilograms, extend the platform a little bit so you can attach the magnet. Okay, use a little tape to attach the magnet. Scotch tape, not duct tape. We don't want the residue. Okay, but that would work. And we can make sure the magnet's nice and aligned. Okay, I'm not sure we're actually going to do the experiment, but you understand how it could be done to get a better estimate of coefficient of friction. Now, what are we doing here? Would we get a high estimate or a low estimate from this experiment, given the squishiness of my fingers? I'm not even sure this is on the screen. Okay. So, I read all this stuff to you before, but there it is. Average angular distance was 1.5 radians. We thought it might be 0.6 or 0.7 the way this looks, if that's really the curve. Okay. And as I commented, we could do some pretty good estimates of these angular displacements. Okay. And do it in degrees because we're used to thinking degrees and then convert to radians, right? And get a really nice curve and do a pretty good job. Anyhow, the average is 0.5 radians per 50 cycles. I'll play it out, we get 25 radians. That's just going out. It also has to come back, and there's friction when it comes back. There it is. Okay, so ask me, what's the analogy to an angular coefficient of friction? Okay. And then switch your fingers. Get a high or low estimate of that coefficient of friction. Now, how would we specify the coefficient of friction? When something is sliding across a surface, it's kinetic friction. Now, this is kinetic friction because the thing keeps moving. I mean, it stops every once in a while. Okay. And eventually it'll stop because of static friction. Okay. But kinetic friction is so low that at that point, your oscillations are probably less than half a degree. And you're not going to lose much out here. Okay, well, now the point is, for U, K, F norm. In other words, your coefficient of friction times your normal force is what you use when things are sliding along surfaces, right? Or rolling friction. And incidentally, I did the same thing with the cart and the incline. Okay, I measured the slope. And I just released the cart, went up the incline, came back, got repelled by the magnet, went up again, came back. Okay, figured out the total distance it went before it dissipated all its energy. And got 0.006 for the rolling friction. Okay, back here. We want to figure out what the angular analog is. Now, what is it? Why do we use the normal force? Because that's what accelerates things. Okay, what is it that accelerates things for rotational system? So we'll use mu k for this time. We don't have to use a different letter. Just mu k times and the normal force, but it's the normal force between the axle and the bearings. Okay. And that's a little bit complicated, but we can treat it as a normal force. And what's that proportional to? That just depends on how many magnets you got stacked on the thing. Doesn't care where they are. Okay. So another question that comes up is, what would happen if I move those magnets out to the end? What would be different? What do you think would be different? I'm actually going to do it just for a couple of cycles. Just take it about a minute. You've got this thing called angular momentum. Now, angular potential and kinetic energy and all that stuff is not that difficult to understand by analogy. It's a little tricky, you got to get used to thinking, but the equations are identical. The relationships are identical. They're just totally analogous to linear motion until you get up to energy. Okay. There are no new quantities, no new units, no new nothings. Except just, getting used to thinking about angular quantities, displacements, and velocities and angular accelerations. Angular momentum, just like linear momentum, is a vector quantity. Momentum of a ball rolling across the table has a magnitude and a direction, right? What's the direction of the angular momentum? If this thing's moving at constant velocity, the angular momentum has to have a constant direction and a constant magnitude. Okay. So what's the direction? Some people want to point this way, some people want to point that way, some people want to point like this, around a circle. Well, that's not a vector that stays constant, is it? Keeps changing direction. Okay, your angular momentum doesn't change. I mean, it does because it's slowing down a little bit now, but it's moving at constant velocity, constant rotational velocity. The angular momentum is always the same. There's no vector in the plane of this motion that mimics the angular momentum. That vector is straight down from this thing. People point straight up, which is close. It's straight down because it's a right-hand rule. You put your right hand, your fingers going in the direction of motion, and there it is. Okay. Well, that's the first thing I'll say about angular momentum. And then if I try to rotate this thing, what happens to the angular momentum? If I try to rotate it that way, what happened to the angular momentum? It changed from here to here. Okay, or if I try to rotate it this way, it'll go from here to here. Okay. Well, angular momentum wants to conserve itself. So I gotta do some work to make that happen. Okay. So I gotta exert a torque through a distance. It'd be a change in torque. Try to take that statement and internalize it so you can build on it. Okay. The other thing is torque. Here's a blob rotating about this point. Okay. That axis coming out. Going in. And here is a force applied at this point. What's the torque exerted by that force? Well, I said the torque, the vector, is R cross F. Where's the R vector? Point in the direction of the R vector. Some of you may be pointing in a direction opposite to the R vector, but the R vector is from the origin or from the axis of rotation to the point of application of the force. Okay? So R cross F is going to be bigger or less than the product of the magnitude of R and the magnitude of F. Well, it's going to be the less because magnitude is this. That's by your definition of cross product, which you should probably review. Because none of you had multivariable calculus. Well, yeah, one of you has. So you should be totally conversant with it. You've got to be able to visualize it. Okay. And what it comes down to is you can take the component of the force parallel to R, and this would have magnitude F sine theta, if theta is the angle between these two things. Okay, because that angle would be the same as this angle. Well, anyhow, you can work that out. The other thing is this force is acting along a line. So if you take a line parallel to the force, the point of application, there is a point at which it comes closest to the axis. Okay. And you could use this R vector on this other blue because as usual, I put that in exactly the wrong place if you like that. Well, this R1 and this R2. Any R vector that goes from here to the line is going to give you the same cross product. The cross product is going to be R cross F into the board. So if I do R anything, okay, put R out here. Any R, it's going to have the same component in the direction of the force as any other R. Okay, now I use force sine theta, the component of the force parallel to R. You can also do the component of R parallel to the force, perpendicular to the force. Okay, yeah, this is the component of the force parallel to R. This would be the component of R parallel to the force. Anyhow, yeah. I'm getting my words mixed up, so I'm gonna shut up here. You can work that out. You should understand cross product well enough to see that. You look at this diagram, see where the sine of theta is, and see where R of sine theta is. Look at that for each of the R vectors that I've drawn there, okay? Where's sine of theta? Where's theta? And you know what I did here, which is totally ignorant. F sine theta is down here. And it's a component of F perpendicular to R, because dot products maximize when your vectors are perpendicular, right? And this is the component of any of these R vectors. The R vector that goes closest to the line is the one that goes perpendicular to the line. And that's going to be the perpendicular component of R, the component of R perpendicular to F. Okay. Again, my words mixed up. So if you work it out, draw your angles and stuff like that, you should convince yourself of that. It'll be very helpful to you for visualizing these torques in other situations we haven't had time to talk about. Now, last thing. As a class, y'all having a hard time getting the problems done. There were a lot of them last week, but most of the ones on the chapter that we're talking about were pretty easy. Okay. One on momentum could be somewhat challenging, especially since we didn't get to talk that much about momentum. Okay. Of course, that means that when I test you, I'm probably not going to ask you the really hard questions about momentum. Okay. Still, it's good for your soul to dig it out and try to do it and overlearn it a little bit, because I might put optional harder problems on the test. If you do, if you got a good understanding of it, that could be very beneficial to you. I'm going to make up, I've already made up most of the study. It'll probably be this evening, hopefully this evening, if not then tomorrow afternoon. I'm going to give you a set of problems that develops these ideas in a sequential way. It's kind of a halfway between text problems and the concept. Okay, develop the concept a little bit, where you do some pretty simple problems, or problems with many bullets. Get a little harder each time, and you give up when you give up, and then you go back and look at it later. Okay. So it's going to be that kind of thing, and they're going to be randomized, so no two people are going to have the same set. Right? But you're going to have the same analysis, be the same. You do it symbolically, it's going to be the same as what everybody else does. Okay, just have different numbers. And I encourage you to get together and think about how to understand these things if you got a chance. That's hard to do because of schedules and stuff like that. Okay, well, we're over time. Got places to go. It's a nice day outside. Try to get out a little bit. Incredible day for November.